Let's dive right into this explainer and decode the universal rules that dictate the movement of, well, absolutely everything around us. I mean, from the moment you wake up, you're just surrounded by movement, right? The fan spinning above your bed, cars crawling through morning traffic, even the satellites quietly circling the Earth thousands of kilometers above your head. They're all obeying this secret, invisible language. So today, we're going to unpack those rules, going all the way from ancient Greek thought experiments right down to the smartphone sitting in your pocket right now. Here's our roadmap for today. We'll be covering 1. The vocabulary of motion. 2. The rules of change. 3. Reading the motion matrix. 4. Why things move. And 5. Motion in the modern world. Section 1. The vocabulary of motion, establishing the building blocks. To really understand this secret language, we first have to define what motion actually is. Basically, it's a change in position over time relative to a fixed frame of reference. But the absolutely crucial point here is distinguishing between your total path and your net change. Distance only cares about the total length of the winding path you've traveled. It's just a number, what physicists call a scalar. But displacement? That's a vector. It has both magnitude and a specific direction. Think of it like this. If you take a crazy winding looping path from your house to a tree across the park, your total distance traveled might be huge, but your displacement is just the length of that straight line from start to finish. And that brings us to the next big difference. Just like distance, speed is a scalar quantity. It's really just a number telling you how fast you're going. Velocity, on the other hand, comes from displacement, which means it always has to include a direction. So traveling 50 kilometers per hour purely as a number, that's just speed. But traveling 50 kilometers per hour towards the north, that becomes a full velocity. Section 2. The rules of change. Uniform versus non-uniform motion. Now that we've got our vocabulary down, let's look at how things actually behave, starting with the two main categories of motion in our universe. First up is uniform motion. Picture a car locked on cruise control on a perfectly straight, totally empty highway. It's covering equal distances in equal time intervals. Since it never speeds up, slows down, or changes direction, its velocity is totally constant. This represents mathematically clean movement with exactly zero acceleration. But let's be honest, the messy, beautiful reality of our universe is non-uniform motion. A bouncing ball losing energy, a race car navigating sharp turns, or just stop-and-go city traffic. These are entirely dominated by non-uniform movement. The speed or the direction is constantly changing, which guarantees one thing for sure, a non-zero acceleration. Now, you might be wondering, how deep does acceleration actually go when we map it out? Well, acceleration is the rate of change of velocity, but what happens when the acceleration itself changes? Physicists playfully named the successive derivatives of position after breakfast cereal mascots. The change in acceleration is called jerk, which is literally what you feel when a driver suddenly hits the gas at a green light. Go further down the rabbit hole and you get snap, crackle, and pop. And these aren't just jokes. They're mathematically real concepts used to ensure the smooth design of things like advanced aerospace engineering and roller coasters. Section 3. Reading the motion matrix, equations and graphs. If you can read this beautifully interconnected matrix of motion graphs, you can basically read the mind of any moving object. On a position time graph, the slope is your velocity. Move to a velocity time graph, and the slope becomes your acceleration, while the area underneath the line reveals your total displacement. It is this elegant mathematical structure where everything is deeply interconnected through the fundamental theorem of calculus. Let's apply this math to reality with a question that actually puzzled humanity for centuries. Which falls faster, a heavy rock or a light rock? Before we had modern sensors, everyday intuition strongly suggested the heavier rock would plummet faster, right? I mean, it just makes sense. But Galileo used pure logical reasoning to counter this assumption. Galileo realized through a brilliant thought experiment that mass simply doesn't affect the rate of acceleration in freefall. And this truth was dramatically proven in real life centuries later. An Apollo 15 astronaut actually dropped a heavy hammer and a light falcon feather simultaneously on the airless moon. Without air resistance to interfere, they hit the lunar surface at the exact same moment. No way, right? But it's absolutely true. Here on Earth, every single object in freefall accelerates downward at a remarkably consistent rate, 9.8 meters per second squared. To put that into perspective, it simply means an object's speed steadily increases by roughly 9.8 meters per second with every single passing second it falls, completely regardless of how heavy it is. This also perfectly explains motion in 2 dimensions. Think of a beautiful parabolic throw, like tossing a baseball. The horizontal and vertical motions are totally independent of each other. The horizontal speed never changes, while gravity purely handles the vertical acceleration. The exact same vector math applies to circular motion. When a car navigates a tight corner, it's constantly changing direction. That means it is accelerating inwards, which is centripetal acceleration. And that feeling of being flung outwards? It's actually not a real force at all. It's just a pseudo force, your body's inertia simply trying to keep moving in a straight line.
Section 4. Why things move, Newton's laws and relative motion. So, we've described the how of motion in exhaustive detail, but now we really need to uncover the deep underlying why. And for that, we look to Sir Isaac Newton's absolute foundation of classical mechanics. His 3 laws explain, well, pretty much everything. The first law, inertia, is why you lurch forward when a bus suddenly hits the brakes. Your body just wants to keep moving. The second law, force equals mass times acceleration, explains why pushing a heavy truck is so much harder than pushing a small car. And the third law is exactly how a rocket can propel itself through the total vacuum of space. By violently pushing exhaust gases backward, the equal and opposite reaction pushes the rocket forward.
Interestingly, this same physics extends to how we view motion from moving platforms, which is known as relative motion. This perfectly explains that delightful illusion where, if you run fast enough through a rainstorm, the diagonally falling rain suddenly appears to be dropping perfectly straight down from your specific point of view. What's happening is your horizontal speed is mathematically canceling out the storm's horizontal wind in your specific frame of reference.
Section 5. Motion in the modern world, from theory to your pocket. For our final section, let's ground all this rich classical theory in the incredibly sophisticated modern technology we rely on every single day. You know those tiny inertial measurement unit chips sitting inside your smartphone right now? They are constantly performing real-time vector addition and calculating derivatives. By using a triaxial accelerometer, a gyroscope, and a magnetometer, your phone silently tracks your every move, step, and tilt. This is exactly what powers features like screen auto-rotation, fitness step counting, and fully immersive augmented reality. Furthermore, this has massive real-world safety impacts. Because our mathematical equations dictate that stopping distance is directly proportional to velocity squared, doubling your car's speed requires 4 times the distance to stop, and tripling it, that requires 9 times the distance. This is exactly why traffic engineers rely on these equations to set speed limits, and why seatbelts and crumple zones are specifically designed to slow down that terrifying physical jerk of a crash. It literally saves countless lives. Ultimately, from a tiny dust particle drifting in a sunbeam to a massive satellite orbiting the Earth, absolutely everything in our universe is bound by this single, coherent matrix of position, velocity, and acceleration. Every single moving object is fundamentally telling a story that can be described using this same small, elegant, interconnected set of concepts. It truly is a universal language.
Thank you so much for joining me on this explainer. I really hope you leave today seeing the messy, accelerating universe around you in an entirely new and fascinating light. So I'll leave you with this. The next time you watch a simple leaf fall or a car taking a tight turn, how will you decode the invisible language of motion happening right before your eyes?